Hey, this is Mr. Weisfeld. I just wanted to go over this velocity time graph worksheet. Uh, One of the standards we're doing this semester is linear motion, and describing linear motion is often done through graphs and charts, tables and things. So let's just review some of those concepts really quickly on this worksheet, and we'll build from there. So you've got this sheet. I got one handy here, but you can see it on the screen. We're asking about this graph here. So let me get my red pen here. All right. First thing to notice is the units over here. Velocity in kilometers per hour. So we haven't been talking about kilometers per hour for a while, but it is just distance divided by time. That's what velocity is, or speed. And distance can be meters, it can be thousands of meters, so kilometers, it can be feet, right? It can be miles. All of those are good units for distance. And time can go, you can use a bunch of different units for time. So seconds is good, minutes, hours, days. You get the idea. In this case, our time is in hours. And I have to admit, 0.1 hours, that's kind of lame, right? But if you think about, let's see here, if you think about 1 hour is 60 minutes, what is 1/10 or 0.1 hour? Well, just divide an hour by 10 and it's 6 minutes. So you want to get an idea of how much time is between these squares. You could say it's about 6 minutes. 1, 2, 3, 4, 5. Okay, so, and those are a 1/5 of 6 minutes. Yeah, you know, don't stress too much. It's just distance. Sorry, it's just velocity versus time in a graph. Let's start with the first question, question number 1. What is the time when the car is stopped? So, if I say that v stands for velocity, I hope that doesn't confuse you too much. When velocity equals 0, that's when a car is stopped. That means it's making no distance per unit time. And so we're looking for, if this is distance right here, if this is velocity right here, then we look across the graph, we see that all these other ones are at velocity at a different time, except for right here, it looks like the car was actually stopped. So you could say right here, the car was stopped from 0.7 hours to 0.8 hours. At what time did the car have the greatest velocity? So let's just look at velocity. And let's look at if velocity starts at 0 and increases, we're looking for the highest velocity. It looks like the greatest velocity was 60 kilometers an hour. In other words, all of this up here is higher than everything else on this graph. So we say 60 kilometers per hour, but the time, I'm jumping ahead of myself here, the time is 0.2 hours to 0.4 hours from the graph. We basically look up from, or look down from where it said it was at 60 kilometers an hour, and we find the time. So we look here to find the speed, the velocity, and here to find the time. What was that greatest velocity? So we said it was 60 kilometers an hour. Hey, and just to be just to be really precise, make sure you put the units there, right? At what time was the car accelerating? All right, so we didn't really talk about acceleration in class yet, so let's talk about it. I mean, define it. We said acceleration is getting faster and faster, or where the speed is changing. Where on the graph is the speed changing? In other words, as time increases, where is the speed increasing? And it turns out, just look for the sloped parts of the curve, right? So let me get a different color here. I'll get blue. So right here we have a sloped part of the curve, right? That means that as time increases down here, the velocity is increasing. Right here we have a sloped part of the curve. As time increases along this direction on the graph, the velocity decreases. So I know it's confusing. We're talking about directions and motion on a graph, but it's an abstraction for motion in real world, right? We'll do that to you a lot in science and math, right? But and then here, as time increases along this axis, my velocity increases here. And then here, my velocity is staying constant. So we're going to ignore those two parts where the velocity is staying the same, which I put in brackets right there. So here, velocity is constant. So let me just write that here. If you're taking notes, this is all I want to see on the worksheet. You don't have to write all this other stuff I've got here. That's just for your information. Just clean up a little bit here. There we go. So the times the car was accelerating, there are actually a bunch. So let's see. You've got from 0 to 0.2, the car is accelerating. And from 0.4 to 0.7, 0.4 to 0.7. And I get you that that's decelerating, that's actually going slower, but and then from 0.8 to 1.0, we are actually accelerating again. So I think I want you to say all of those here, because the question is, at what times was the car accelerating? And so by using this dash, I can specify all times between 0 and 0.2, 0.4, 0.7, etc., etc. How fast was the car going at 1 hour? All right, so this is not 1 hour. That's 0.1 hour. This right here is 1 hour. So all you do is go up from 1 hour. You see that you get this point right here. Then you go across from there, and you see the car that was going 40 kilometers an hour. So 40 kilometers an hour. And then what was the acceleration at 0.9 hours? Okay, so the acceleration at 0.9 hours. So acceleration, we said, was going faster and faster. It's faster and faster as time increases. So its acceleration is actually a change in velocity divided by a change in time. And hopefully the little change in triangle is not confusing to you. But change in time means you take a final velocity minus initial velocity and divide it by final time minus initial time. You have probably seen this before when I say that the slope of a graph, m, now a little bit of math, sorry, Mr. Weisfeld can teach math too, delta y over delta x, so that's rise over run. and that equals y final minus y initial all over x final minus x initial. Alright, so sorry about that, a little bit of math, but the point is, this equation right here is talking about y over x. This equation right here, v, the velocity is kind of like y, and t is kind of like x. So the slope of a velocity time graph is actually the acceleration. And the way you can maybe remember that is look at the parts of this graph where we had no acceleration. So we said that here, get another color, we said that here velocity was constant. Do you remember this part of the graph here? What do you notice about the slope of that segment of the graph? The slope is flat, which means 0. That means when velocity is constant, acceleration is 0. So slope, which is acceleration, is 0, where velocity is constant. Hold on to that. We'll run into that again. But since this is, let's get back to F here. Since this is a flat line, no, since this is one straight line from 0.8 to 1.0, it is actually the same slope everywhere from 0.8 to 1.0. That means you have constant slope, which is constant acceleration. Constant slope implies constant acceleration. All to say that I can take the velocity final, which is 40 kilometers per hour, minus the initial velocity, which is, so here we go, I'm picking these 2 points to figure out my slope of that line. We already said that this point right here was 40 kilometers an hour, and it's at 1 hour. So 40 minus this point is 0, and it's at 0.8. So 40 minus 0 all over 1 minus 0.8, which equals 40 divided by 0.2, which equals, I think, 200. So the acceleration was 200. 40 divided by 0.2. Let me get the calculator just to be sure. Don't want to mess up. 40 divided by 0.2. 200. That just seems fast. But yeah, 200 kilometers an hour is fast. So the acceleration is 200 kilometers per hour. But acceleration per hour per hour. Oh, Mr. Weisfeld, why you do this to me? That means every hour, this object, car, right, is going 200 kilometers an hour faster. That's why you have, so it's kilometers per hour squared, or kilometers per hour. Acceleration has time squared in it, in the bottom. All right, so let's go to the next question here. The following table shows the position of 2 cars at the times indicated. Graph the data for each car on one set of axes and compute the velocity of each car. Okay, so car A at 0 minutes is at 0 kilometers. So I'm going to plot car A in red. And then I'll come back and do car B. So car A is 0, 0, that's right here. Then at 2 minutes, so this is minutes right here. So this is kilometers per minute now. At 2 minutes, it's 2 kilometers an hour, so right here. At 4 minutes, it's 4 kilometers an hour. 6 and 8. It's 6 and 8. So let's do this. 6 and 8 is 8. All right, I think I can draw a straight line here with my cool little program. So let's just do a straight line here. Okay. Sorry to geek out there a little bit. All right, so now the next one I'm going to draw is I'm going to draw it in blue, car B. And I know it also said find the velocity or the speed of each car. I'll do that in just a second. So at 0, car B is going, it's at 2 kilometers. So at 0, it's at 2 kilometers right here. And then at 2 minutes, it's 3.5. 2, right in the middle would be 3. 3.5 would be right in the middle here. So I'm thinking this is where we're at. 3.5. At 4 minutes, we're at 5. So this is 4. Right in the middle is 5. So right here. At 6, we're at 6.5. So this is 7. 6.5 is halfway in between. At 6, we're right here. And then at 8, we're at 8. So these graphs actually overlap at 8. So let me get a line here and draw a little bit of a line here. Okay, so you should have graphs like that. One for car B, one for car A. Then we're finding the speed of each car. Remember that what we said was speed or velocity is distance divided by time, or change in distance or position versus change in time, you could say. All I need to do is take 2 points, say a final position minus an initial position over a final time minus initial time. And I could, since these are straight lines, I could take any 2 points along here. And I'm doing car B first, so let's do this. Let's do this position, 8, minus initial position 2, minus 2, divided by the time, 8 minutes minus 0 minutes. You got me? So that's 6 divided by 8. So that's 3/4 of a kilometer per minute. That's car B. So let me ask you a question. Which car is going faster? Which car seems to go farther in the same amount of time? If you said that steeper slope equals faster, why don't you give yourself a pat on the back? Because that's exactly right. It turns out steeper slope is faster. So as the slope goes less steep, In other words, as it goes flatter, objects are going slower. So I would expect the red car to be moving at a faster speed than 3/4 of a kilometer per minute. So let's get my red pen out. And let's do the speed of the red car. The speed of the red car is distance divided by time. That equals final position minus initial position divided by final time minus initial time. Sorry, ti. So if I pick these 2 points again, 8 minus 0 this time. So 8 minus 0 all over 8 minus 0. Same thing for the time. I'll just circle it again. I picked the same points to figure out the speed. It's okay as long as you keep these points together in your calculation, right? 8 over 8 is 1 kilometer per minute. So is 1 greater than or less than 3/4? It's greater than, right? So the red car is going faster than the blue car. And that means the slope of the position versus time graph is greater than the slope of the blue car's position versus time graph. So greater than blue. So you should have a couple graphs here. You should have a calculation of speeds. And if you didn't get those, you can write those down. You can review those. It's great. All right. Let's go to the next page and then we're done. Draw a velocity time graph for a ball that has been thrown straight up in the air and returns to its original position. So what I'm going to do is I'm going to let me put down a couple of lines here that I want to be my 0 lines. So this is and then let me draw another one here. These are my axes. I call this, remember when I say velocity versus time graph, I want to have time here along the x-axis, and then I want to have velocity over here on the y-axis. It's not the same as a position versus time graph. Some of you guys I saw were doing a position versus time graph. And I'll do that also just for good measure. But let's say when you throw something up in the air, what happens is your hand has to give it an initial velocity. We talked about that on the energy worksheet. That's basically here. This is an initial velocity. Positive, up. I'm throwing the object up into the air. So here's a little stone or something. This is the velocity vector. It's going up in the air. What happens as that object goes up in the air? Is it at the next fraction of a second later, is it going faster or is it going slower? Okay, I think you could probably convince yourself that it is going to be going slower as we throw it up in the air, because gravity is slowing it down. It's working against that object's motion. So let's say gravity is making it go slower and slower and slower. So as time goes on, my velocity is getting less and less and less until my object gets to the top of its motion and it stops. So at the top, velocity equals 0. Every object that you've ever thrown up your whole life stops, turns around, and then comes back down. That's the way things are. So as soon as it turns around, is it going immediately faster again in the positive direction? Is it going faster up again? No, it's going faster down. So this is what we call negative velocity. So it starts off a little bit less. The velocity starts off small but negative. So the velocity then gets increasingly large, negative. It's speeding up as it comes down. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And when it hits your hand, it should be going about as fast as it was when you let it go. So here it comes back. Here's your hand, and it's going about as fast as it was when you let it go. So this is negative v. This was a little vector sign to say that, but let's not do that. Let's just talk about plus or minus v. So now if I draw this graph and let me put a line in here, I basically have a line that goes from where you threw it to where you caught it. Velocity is always decreasing. Okay, so here's what a position versus time graph looks like. And I'll draw that in blue. So those of you who drew this, I applaud you for that. You can draw this as well, maybe for a little extra credit. So what happens when you throw it in position is it starts off, it's going to get to the top here. I'm going to draw it on the same graph because when the object gets to the top of its path, the time is 0. So it's going to go up like this. 0 velocity, turn around and come back down. And then when it hits your hand, it's going to look like this. So now here's the interesting thing. As you're looking at this graph, it turns out the values of this curve are the slopes of the position graph. So this is, let me put it in blue, position versus time is in blue. And position versus time has this parabola shape because it's accelerated motion in one direction. That means it initially starts off going faster here, and then as it gets slower, it doesn't get slower very quickly. It gets slower relatively slowly. Okay, so that was number 3. Let's do number 4. Okay, a police car is stopped at a red light. As the light turns green, a diesel truck hurtles past in the next lane, traveling at a constant speed of 28 meters per second. All right, so let's do this. I think when I counted this was 28 meters. I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. All right, let's draw my axes here. I'm going to draw them in black. So this is my axis, my y-axis. Let me get this over a little bit here. Let me draw. That's my velocity axis, and this is my time axis. So all right, so they want us to draw a velocity versus time graph. So this is time, and this is velocity. The units are meters per second, and this one is seconds. So, police car is stopped at a red light. Let's draw the police car in red. So, it's got 0 velocity at 0 time. The light turns green at 0 time, and a diesel truck is going past in the next lane at a constant speed of 28 meters per second. So this, I counted, was 28. So this is 28 meters per second. If the truck is going at a constant speed, what's the slope of the truck's graph on the velocity time curve? So actually, let's draw the truck in green. So if the truck is going at a constant speed, its velocity looks like this. So from light turning green, it's going over here, and it's going 28 meters per second, like that. So the truck is just cruising along. Its velocity at every time is basically 28 meters per second. So this is all 28 meters per second. This is constant speed. So this is a flat line. All right. If the police car accelerates at 4 meters per second, how many seconds does it take to catch the truck? So what you do is, here is one way to interpret 4 meters per second. So this is 1, 2, 3, 4 meters per second. That means every second the police car is going 4 meters per second faster. So it's just over 1 up 4 every second. Over 1 up 4. Over 1 up 4. So what you should do is you should say it took 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6, 7, 7 seconds for the police car to catch the truck. So that means 0 to 28 meters per second in 7 seconds. You could convert that to miles per hour in how many seconds. And I don't know if that's 0 to 60. It might be. I could figure it out though. And so let's draw in that the police car will basically intercept, because it's going to try and pull the truck over, right? In about 7 seconds. So you can draw this line right here, and this is the police car's velocity versus time graph. So, how many seconds will it take the car to catch the truck? Turns out 7 seconds. And of course, that's why police cars have, some serious acceleration. All right, so if you wanted to correct this, or if you wanted to do it for the first time, turn it in for some credit, you're welcome to do that. Thanks for listening.